Hello everyone, good evening. So today's session is about invertible functions. And since we have already discussed composite functions, so this is the base of invertible functions. If we know about composite functions, then only we can proceed to invertible functions. If you haven't seen my previous videos in which we are discussing about composite functions, then please do watch the video. So let's proceed to invertible functions. So does a function have its inverse? And what is an inverse function? And when a function is called invertible? So to know about invertible function, first of all we should concern about composite function and bijectivity of a function. And bijectivity of a function is nothing but whenever a function is both one and onto, then this function is called bijective. Again, composite function we have already discussed. So the definition of invertible function is a function. Suppose the function is f from a to b is called an invertible function when there exists another function z from b to a such that here we have two conditions. The composite function of f and z and z naught f equal to identity function in the domain D and in the domain A. So if we have a function f from a to b, then if there exists another function z from b to a, we have a function from a to b. Now we should have another function z from b to a. That means here codomain is b, but in this case here b is the domain and a is codomain, the reverse of this function, such that they are composite functions. Composite function of f and z for equal identity function d and gof z naught f equal identity function a. So basically, whenever we take a function, suppose f from a to b, if we have another function z from b to a, if these two functions satisfy these two conditions, f naught g equal identity function and g naught f equal identity function, then only we can say that this function z is nothing but the inverse of this function f. And in that case, this function f is called an invertible function. So if these two conditions are fulfilled, then only we can say that f has an inverse function, which is z, and or we can say f is an invertible function. There is a point to be remembered. Here, the functions f and z, these two functions should be bijective. There is a theorem based on this definition of invertible functions where we can show that f and z are bijective when we have an invertible functions. But we will discuss it later. Now come to this definition. A function f from a to b is called an invertible function if there exists another function z from b to a, and if these two functions satisfy these conditions, then only we can say that the second function z is the inverse of the first function f, or in other words we can say f is an invertible function. So I hope it is clear. To know these invertible functions, I have an example. Let's go through it. So this is the question related to this function. Let f from R to R be defined by f of x equal to x plus 3 so that f is invertible, and find f inverse, and f inverse goes from R to R. This is obvious. So we are given a function f from the set of real numbers to set of real numbers. Be defined as, this function is defined as f of x equal to x plus 3, then so that f is invertible, and also find f inverse. Now if we see the definition, a function is called invertible when if there exists another function goes from b to a such that these two functions satisfies this condition. First one is fog f not g equal identity function and gov equal identity function. So if we can fulfill these two conditions, then only we can find an inverse function. So for the solution, our first step is to find the function g, another function g. We are given f from R to R, and it is defined as f of x equal to x plus 3. So f of x is nothing but y. Since f of x is the inverse of the element x in the domain, so I can write that f of x is equal y. Y equal twice x plus 3, right? Since we have to find the another function z according to this definition, so I express this x in terms of y, because this is the expression where y equal twice x plus 3, but I want to express as in terms of y. Now twice x equal y minus 3. Therefore x equal y minus 3 divided by 2. So this is the first step to solve such questions. Since we have to find the another functions, therefore I express this x in terms of y. So here I got x equal y minus 3. Can I write this x in terms of z of y? Can I write? Obviously we can, because this expression x equal y minus 3 by 2, it is a function of y only. It is a function of y only. Whenever we put the values of y, we can get x. So we can say that this x is another function of y. Therefore, I have the another function as z of y equal y minus 3 by 2. Therefore, this is the first step. This is step 1. We have found the function z of y equal y minus 3 by 2. Now step 2. Since in the definition fog equal identity function and gov equal identity function, therefore here f not z equal and z not f equal what? So f is a function from R to R and z is a function from, here I have taken z, but z is nothing but the inverse. In the question we have to find the inverse of the given function, so I have taken another function z according to the definition of invertible function. So if this z is nothing but f inverse. Here in the question we are given that this is f inverse. So in this function z of y equal y minus 3 by 2, it goes from R to R. Because in the definition, whenever we have f from a to b, Then we find another function from B to A here, R to R. The function Z goes from R to R. Therefore, this F naught Z will be what? Identity function in the domain R. Since here domain and codomain are same, therefore fog will be equal IR and gov will be equal IR. But how these terms come? How this is equal IR and how this is equal IR? I will show. So how this is done, how this is proved, how we know that fog equal identity function R and gov equal identity function. So I will show you here. Now we find fog. Since f naught z is a composite function from R to R and z is the function where zy equal y minus 3 by 2, there I will take f naught z of an element in this function y. Then by definition of composite function, this is f of zy. And z of y equal what? Since z of y equal y minus 3 by 2, I put it here y minus 3 by 2. Again, the function f is also defined in the question. So f of y minus 3 by 2 will be what? Since f of x is twice x plus 3, therefore f of this element will be 2 into this element plus 3. According to definition, 2 into y minus 3 by 2 plus 3. Now 2 cancels out. Finally, we get y minus 3 plus 3, and this is nothing but y. We all know that in last videos of mine, so I have told you what is an identity map. So since f naught g of y equal y, that means composite function of this element is nothing but that element itself. So this function is an identity function. So f naught c is an identity function and we denote it as IR. Since here the domain and codomains are real numbers, set of real numbers, therefore f naught g of y equal IR. Right? Now to see the next one, how g naught f equal IR. So I am showing it here. Z naught f, and z naught f is a composite function of the functions f and z goes from R to R, and we take an element in z naught f in the domain x. Since by definition z naught f of x is equal to z of f of x, and f of x is nothing but f of x equal to x plus 3, so replacing it here, 2x plus 3. Again, z of y was defined as z of y equal y minus 3 by 2. When we take the element y, then z of y equal y minus 3 by 2. But here this element is twice x plus 3. Therefore, by definition of this function, twice x plus 3, suppose this is the element capital A. This minus 3 divided by 2 by this definition, right? Suppose this is a single element. Z of y equal y minus 3 by 2, right? Now, plus 3 minus 3 cancels out and twice x by 2 is remaining. Now, 2 also cancels out, so the element is x. Again, by definition of identity map, z naught f of x equal x. That means this composite function z naught f is an identity map, and we denote it here IR. We already discussed that what is an invertible function. If a function goes from a to b, then if there exists another function z from b to a, and if these two functions satisfy two conditions, fog equal I and gof equal identity function, then only we can say that the first function f is invertible and second one is the inverse of the first one. So here, since f naught g is IR and z naught f is IR, therefore I can say that the function this f is an invertible function by definition. Therefore, the function f Therefore, the function f is invertible function. So, I have showed that we are proof that this function f is invertible. Also, we are to find what is f inverse. But in the definition of invertible function, I have repeatedly said that if we have the second function z and if f and z satisfy the two conditions f naught g equal I and z naught f equal I, then the second function g is called the inverse function of the first one. So here I have proved it that this function f is invertible, and we have got another function z of y equal y minus 3 by 2, right? Is it y minus 3 by 2? Yes, it is y minus 3 by 2. So this will be the inverse of this f. So here I can write the inverse of f is inverse of a function f is always denoted as f inverse. F inverse. And this f inverse is nothing but this, or g of y equal f inverse, and this is defined as y minus 3 by 2. And what is the domain and codomain of this inverse function? This is nothing but f inverse goes from R to R, or we can say Z goes from R to R. So this is the inverse of the function f. So this question is done, right? So I hope the definition of invertible function is it is crystal clear. So again, there are two theorems related on the base of these invertible functions. The first theorem is, if we have a function f from a to b and z from b to a, the two functions such that their composite function z dot f equal identity function in the domain A and f naught z equal id, then the function f and z are bisective. Then the function f and z are bisective. So this is the first theorem. If a function f from a to b and z from b to a be two functions such that their composite function is equal ia and fog equal ib, then the functions f and g are bisecting. So bisective is what? Bisective is nothing but when a function is both one and onto. If we can show that f is both one and if we can show g is both one and onto, then only we can say that f and g are. Let us take two elements x1 and x2 in the domain A. Then their images f of x1 and f of x2 will be belonging to B because f is a function. So we have to show that f is 1, 1 and onto. Now for that, let us suppose f of x1 equal f of x2, right? Now taking z on both sides of this f of x1 and f of x2, g of f of x1 and g of f of x2. So, and we know that g of f of x1 is nothing but c naught f, the composite function c naught f of x1. And here, g of f of x2 means c naught of x2. Since g naught f equal IA, g naught f equal identity map IA, therefore we can write IA x1 and IA x2. Since IA is the identity map, so we can directly write or say x1 equal x2. Because by definition of identity map, I of x1 should be equal to x1 and identity function of x2 should be equal to x2. So when we let f of x1 equal f of x2, finally we get x1 equal x2. That means this function f is 1. So we have done f is 1. Right? Now to show how this f is onto. Let us take an element x1 in A or x in A. Let us take an element x in A. Then here exists y belongs to B such that f of x equal y. Such that f of x. Consequently, g of y equal, and y is nothing but f of x. And g of f of x is also, we can write it as g naught of f of x. And g naught f is identity map IA. And identity map of an element, it is the element itself. So finally we get g of y equal x. That means for an element x belongs to the domain, we get another element y such that g of y equal x. That means g is onto. Therefore, g is onto. I have shown only what f is 1, 1, g is onto. But we are not showing already f is onto and g is 1. So this is also important. We have to prove that f is onto and g is 1. Then only we can get that this function f and g are bisecting. So for next we have to show g is 1, 1 and f is onto. Now first I will show g is 1, 1. Let x1 and x2 be two elements in B, then there exists z of x1 and z of x2 in A because z is a function from B to A. Then let us take z of x1 equal z of x2 because we are going to prove that z is 1, 1. Now, taking the function f on both sides, f of g of x1, f of z of x2, and f of z of x1 is nothing but fork of x1, f naught z of x1 and f naught z of x2. Again, in the theorem we have f naught z is identity function A, right? In the theorem we have f naught z equal id. So I write it here, id of x1 equal id of x2. And by definition of identity map of an element is nothing but the element itself. So this implies x1 equal x2. Since we have taken z of x1 equal z of x2 and we finally get x1 equal x2, that means this function z is 1, 1. Therefore, z is 1, 1. Now, to show how f is onto. Again, let x belongs to B. Then there exists another element y belongs to A such that z of y equal x. Consequently, f of x will be what? F of x will be f of zy because x equals zy. Now f of z of y is nothing but fork of y, f naught z of y. And f naught z is equal id already given in the theorem. Again, by definition of identity map, id of y will be the element y itself. So finally we get, if we take an element x belongs to B, then there should be another element y belongs to A because z is a function from B to E such that z of y equal x. Consequently, if we take f of x, then we can write f of z of y because x is nothing but z of y. Then finally applying the condition of composite function, we get y. Since f of x is equal to y, that means f is onto. So what we have got, since f is 1, 1 and onto, z is 1, 1 and onto, we know that whenever a function is both 1 and onto, then only we can say that this function is bisective. So here f will be an bisective map. And C also is an bisective map. So in the statement of the theorem, what we have, if f from a to b and z from b to a are two functions and f naught z equal ib and z naught f equal ia, then what, f and z are bisective. So first I have shown f is 1, 1 and z is onto. Then again I have shown z is 1, 1 and f is onto. Then finally I can say f is both 1, 1 and onto, so it is bisective. Similarly, z is both 1, 1 and onto, so c is bisective also. So the theorem 1 is done. And there is also another theorem which I will show you in the next session. So that's all about this video. Thank you for watching.